This video is about deep dive comparison of the instruction sets of the ARM and x86. We will go through a lot of interesting things, and it's actually not so simple to compare instruction sets. And on the internet there is a lot of kind of nonsense information. So we will go through really interesting stuff, and I will show you that we will go through the x86 instruction length distribution, because it's a variable length. So we will go through some data. We will compare how much saves the variable length, the binary code. We will take a look also on the coding of the instructions. The ARM has a fixed width and x86 has a different, has a variable, and how is it? And you can see that it's much different here. And we will go through all the data, and also we will compare the architecture registers, which has a great influence for data shuffling and IPC. So we will go through the data, and this is actually the measurement. We can see, we will compare the ARM and x86 on different workloads, and there is a great study, like more than 50 pages in the PDF, and there is a comparison and the direct influence of the instruction set for IPC. So we will compare ARM, we will here compare the ARM alpha, and this red is x86 in the graph, so it's really interesting. Then we will compare also the floating point, single instruction, multiple data units, and the instruction set extensions. So we can actually, we will compare the SVE2, which is up to 2048-bit wide, into AVX512, which is also very interesting, and we will take a look on the subsets for each one. This is the AVX512, and we will also compare the, let's say, old Neon instructions to brand new SVE2 instruction set. So, and what's the performance and so on. And I'm going to start a comparison with the biggest lie which is spread on the internet. And the biggest lie is spread that that ARM is the RISC and it needs much more instructions to do the same work than x86, which is the CISC. And this is not true. Actually, there are some differences, but the difference, we will go to the numbers, and I will show the measured numbers, and I will spread this lie. I will actually break this myth down, and I will show that the difference is really small, and you will be surprised. So, but to start with, ARM is not typical RISC actually, because typical RISC is like a MIPS 32, which has like a 87 instructions. ARM has a much more, it's like hundreds and hundreds instructions. It's really similar to the CISC. So in terms of complexity, it's really similar. And ARM instruction set, when they designed the ARM in 2010, they took both the best things from the RISC and the CISC and then combine it together. So ARM is more like a hybrid than anything else. So let's take a data, and you will be probably really shocked. And this is actually the table from Andre Furmusamo from his Twitter. And it's really interesting because this is the spec 2006 benchmark, and it's profiled, and there are, you can see here the instructions count here. For every subtest, you can see the instructions, and you can see Apple A12, which is the ARM, and Intel 9900K, which is the Coffee Lake refresh CPU architecture. And so it's a ARM versus Intel, and you can see there are different number of the instructions. But in overall, for whole benchmark, you can see this is the final actually number of the instructions when you run the benchmark. And you can see here the difference. And the difference actually is less than 10%. So when somebody says that you cannot compare IPC between the ARM and x86 because of course ARM has a different number of the instructions, it's not true because the difference is less than 10%. So it's not like ARM doesn't have like 4 times more instructions than x86. It's just the difference is less than 10%. So there is small difference, but it's not something significant. And especially when you look at the IPC, the Apple here has a 70% IPC higher than Intel. And if we take a look on the performance per cycle, because there is a 10% more instructions for the same work to be done. So the overall performance is only 65% better per cycle than on the Intel. So yeah, when somebody talks about the IPC and measures only and takes into account the performance and divided by gigahertz, which should be called PPC, but most of the people call it IPC anyway. All the smart people which are saying that ARM is RISC and has a 5 times more instructions are totally wrong, because actually the discrepancy is only about 5%. And when you are comparing two ARMs or ARM, I don't know, Cortex A77 to Zen 2 or the Intel, which has a really similar PPC, so it's actually like 1 or 2%. So it's like on the edge of the error. So yeah, you can actually say that the IPC is almost equal like a PPC. So all those people, they say the ARM has a different number of the instructions than CISC, like a much more than 2, 3 times, 10 times maybe. They are totally wrong. So you can see that this is the biggest myth this is created about around the ARM, and it's totally not true. And yeah, to support this, I will show you also that everybody knows that a modern x86 CPU has runs internally as a RISC CPU, because it's actually the execution cores, the backend is executing micro-ops, which is kind of RISC, and it's since K5 and the P6 architecture. It's like a 90s. So it's really old, and ARM has a decoder too. So I will show the PDF actually. This is Cortex X1, and you can see here Cortex X1 has a decode unit. So yeah, so even it's a RISC, but it has a meaning there is a decode unit. It means it must be decoding the instructions into something even smaller, right? Yeah, so the difference between the x86, which also has a decode from the x86 to the micro-ops. So yeah, both of architectures has a decode unit. Just because ARM is the instruction set is RISC already, there is a less actually complexity to do the decode. The next thing I would like to talk is a number of the architecture registers. And before we will talk about the registers, just to note that Apple has a much higher IPC than actually Intel and AMD. And because this is really related to the also how many registers you have available. Okay, let's see actually the table. This is the summary table, and you can see here that the ARM has a 31 general purpose registers, while actually x86 has only 16 of them. This is like a half only. And in terms of floating point registers, which is more related to the SIMD, let's say single instruction, multiple data, which is not only a floating point, it could be also integer, right, in the vectors. So ARM has an advantage of 32 registers again, and x86 is, most of the CPUs is limited to 16 again. AVX512 has a 32, so but only few CPUs has a 32. And so let's take a look closer on the comparison. I found some pretty nice tables. So you can see here that ARM here has actually 32 registers for the general purpose, but the last one is not is used like a zeros. It's a kind of special, but you can normally for the computation you can use only 31, and for the floating point there is a 32 registers. In comparison, x86 has only 15 or 16 actually, and 32-bit had only 8 registers. And in the SIMD unit, it's really similar also, 16 registers, and in the 32-bit only 8 registers, which is kind of related to the floating point here. And it has a direct impact to actually for the IPC. And if somebody says it's not, it's kind of lie, because if a number of the architecture registers has no impact for IPC, then why actually Jim Keller and AMD designed the AMD 64-bit extension? Why they increase the registers from 8 to 16? Doesn't make sense, right? When there is no influence for the performance. No, it has a direct influence to performance. So yeah, more registers is better. And why it's better? Because just imagine that you have a algorithm which every loop you need to, it's optimized to use actually maybe 30 registers, right? And then you have a jump to the beginning and start another loop of the calculation. And the problem with the only x86 having half of the registers, the same algorithm in the middle of the loop will be like out of the 3 registers. And it will need to store some data and load the new one in the middle of the loop. So actually, instead of ARM is able to run actually the loop with only calculation instructions for the integer and whatever floating point, but mostly without any load and stores. But because not enough registers, the compiler and x86 has to do more loads and the stores in the middle of the loop. So this is the direct impact for IPC. And of course, you can say that there is also physical register file. There is so CPU has a much more registers than actually the architecture is accessible. But you have to remember that those physical registers, which is like 160 of them instead of 16, So, but you have to remember those registers are used also for renaming stage, for our out of order engine, for removing the false dependencies, and so eliminating the bubbles in the pipeline. And also you have to remember that when you do avoid this data shuffling, you have to have a special logic and special transistors invest to detect this data shuffling. So instead of unloading to the memory the data in the middle of the loop and loading new ones, you are using the physical registers, but the CPU has to detect this behavior, has to kind of use the physical registers. And it costs you the transistors, and it costs you also the energy which is burned to detect and everything. So it's not so easy actually. So that theoretically you can get over this disadvantage somehow, but it costs you that the compiler is producing the code which has a lot of data shuffling in the binary, and the CPU, x86 CPU, has to kind of detect those behavior and burn the energy to eliminate it. So this is huge thing also. This is both actually increasing the IPC and also increasing the efficiency. So this is also why ARM instruction set is more energy efficient. When I'm talking about the IPC, let's take a look on the picture with the actual ARM versus x86 CPUs in the IPC. This is the Geekbench actually data. Geekbench score divided by gigahertz. So this is the points per gigahertz, which is PPC, IPC, because we know that the IPC is almost the same like a. So, and let's take a look here. 2020 here. This is the year to compare, and we can see that the Zen 3 is only slightly better than the Tiger Lake. Apple A14 is like a way better in terms of IPC. It's like a 60-70% above Tiger Lake and Zen 3, and the ARM X1 has a higher IPC, much higher IPC than the Zen 3, which is the consumer smartphone core, and the server core, the Neoverse V1, is like a 50% above Zen 2, or the Neoverse N1, which is somewhere here. So you can see that this is another proof that the ARM is really related to the higher IPC, just also because of better instruction set. So don't forget this. Now let's take a look on and compare the instruction coding, because this is also really interesting. Instruction coding is actually, ARM is typical RISC, which is fixed 32-bit wide, which is 4 bytes. And on the other hand, x86 is typical CISC, which has a variable length and could be theoretically 1 byte to 16 bytes, but I found some really interesting table which actually shows the distribution, which is of course depends on the different code, but this is a typical distribution of the instruction length in x86 code, and you can see a lot of instructions are much shorter than 4 bytes. And remember, this is the ARM. ARM has always 4 bytes, which is 32-bit, and x86 has an advantage because it's using a lot of shorter instructions. So you can save some space, right? But there is also some instructions which are much longer, up to 11 bytes. But when you do, you can see in the text, when you do multiply the number of the instructions, the shorter ones, you will see that 53% of the code is the shorter ones, and like 47% has a longer than 4 bytes. So in the reality, the savings of the space is not actually that big. And I found, let's take a look on another data I found some on forum, and they are comparing the same code which is compiled for different targets. And you can see here it's actually the 32-bit x86, 64-bit here, 64-bit ARM, and you can see there is a difference. So you can see, yeah, you can see here ARM has a typical 4 bytes per instruction on average, and you can see here the x86 has a 3.45. And when you do the ratio and calculate, you will end up that x86 is actually saving some space, like a 16%. Respective, ARM binary code is 16% larger. So it's not much actually, because this penalty is relatively quite small. If it would be like a double and double throughput for the memory and double savings on the hard drive for the code, this would be really something probably there is a lot of benefit if it's really double savings, but it is just the 16% savings. This is big question, and my conclusion is that it's really not worth of such a complex actually design, and I will explain actually why. And this slide shows the difference between the coding of the ARM on the left side and the coding of the x86 on the right side. And you can see here that the ARM is using 32 bits, the fixed coding. Actually, there is some 14 different codings, but always it's a 32-bit wide. And on the other side, you can see x86 here. And you can see here, there is 4 different prefixes, and each of them could be there and could not be there. So it could be 0 to 1 byte actually. The only thing which is mandatory is the opcode here, and it could be like a 1 or 2 bytes, and everything else here is it's again optional and doesn't need to be there actually. So it's really variable length, and you can imagine how much energy it costs on the decode in the front end of the CPU. There is you can if you calculate the possible combinations, there is like probably hundreds of the combinations here. So yeah, it's really complex. It's really complex, and the question is if it's really worth, because it makes a problem that when you do the program jump somewhere, you don't know where. With the ARM is really easy. You know that 10 instructions backwards jump. That it's like 10 instructions multiplied by 32 bits. But with the x86, to make some jump in the code, it's variable length. So you never know where the beginning of the instruction is actually. So it's really complicated. And it brings only 16% of binary savings, which is like today when we have a gigabytes of the RAM and terabytes of the SSD drives, it's like really funny. And my conclusion from here is it's probably not worth for the more transistors to detect actually the variable to decode, and more energy is burned to decode this variable length of the instructions. So you can see ARM is simple, faster, and also it consumes less transistors and less energy. And this is really important. I have to note that for people, they think that this variable coding and really energy inefficient thing of the x86, it's really good that they've saved 16%, like in this picture. So yeah, I can tell you that Apple CPUs, they use memory compression, which can bring you like a 40% savings in the space, in the binary, in the memory actually. So the ARM is actually, the Apple ARM CPUs, they do eliminate this 16% disadvantage and turn it into like a 25% advantage for the ARM, because it so Apple cores, they are saving transistors and energy on the decode for a simple instruction set, while actually increasing the bandwidth and saving the energy, and have a small binaries, because they are using the memory compression, which is totally really reverse. All the struggling for the x86 is kind of wasted because of really smart techniques like a memory compression. This is kind of off topic, the memory compression here, but it's kind of big thing actually. It's patented by Apple. And if we take a look on the slide from the NVIDIA presentation, which is called Energy Shopping List, you can actually see here that how much cost actually the double fused memory accumulated calculation energy. And you can see on 10 nanometer it cost 7.6 picojoules. And in compared to 10 millimeters, the wire energy for the communication, it costs much more than actually the calculation. And so yeah, do not underestimate actually the access to the memory. You can see the drum interface energy and drum access energy per 1 bit. If you multiply it by 256 bits, it's a lot of energy actually in compared to calculate 256 bit calculation. So the communication to the memory, it costs a lot of energy. So this is actually the reason why Apple developed such a difficult thing, and why they do the memory compression. They actually eliminate the disadvantage of the ARM slightly bigger binaries and turns into the huge advantage in the saving space and the throughput, and also saving a lot of energy and a huge amount of the energy. Of course, not maybe useful for the desktops, but in the mobiles, in the smartphones, definitely it's like a killing feature, you know. So let's go for another comparison here. And this comparison is actually the number of instructions. And this is, by this I will destroy another myth which is around ARM. Because ARM is not typical RISC, because typical RISC, let's say x86 has 1300 instructions, which is really complex, and it is good because more really good instructions, it can increase the performance a lot actually. So this is really good. And speaking about the very useful instructions, you can see here 2013, which were introduced the TSX, the transaction memory extension. And this is actually the special instructions. They help to speed up the multi-threaded programs, and a lot. The typical multi-threaded applications can be speed up by 40%, which is a really huge number. And like a SQL databases, they could be speed up by factor 5 or 6. So this is a huge speed up for some server loads. So x86 and Intel, they did a really good job. So let's do not underestimate x86. They have a pretty good and useful instructions. So a lot of good instructions which can bring really incredible number of the performance. This is really every modern instruction set should have actually. And but you can see here there is an equivalent. ARM introduced transaction memory extension, which actually does the same thing as TSX in x86. So you can see ARM actually is keeping the pace for those really useful server grade instructions. So yeah, there is no wonder that ARM has around 1000 instructions. So yeah, it's not a RISC. It's not reduced like a 80 instructions instruction set. There is a 1000, close to 1000 instructions. And if you don't believe, just take a look. Take a look on the some PDF. I will show you actually this is actually the instructions of MIPS 32, and it has a less than 90 instructions. And this is a typical RISC actually. Less than 90 instructions. This is the basic instructions. So yeah, this is not 1300 instructions like x86, right? All the prefixes and the variable length complex instructions. So it's like a really simple. But let's take a look on ARM, and let's take a look on the X1 core. This is actually the software optimization guide, which I recommend to everybody, because you can see here kind of architecture of the CPU, which is showing like a 4 LAUs, 2 branch units here, so it's like a 6 wide, so it's much wider than AMD and Intel. It has a like a 4 floating point units and 5 memory units. And this is the first CPU which is able to do 3 loads per cycle. This is really no x86 core can do 3 loads per cycle. This is the monster core actually. Even Apple cannot do 3 loads per cycle, as far as I know. So this is really really interesting document actually. And but there is also the number of the instructions and how many of them can be executed, the throughput. So you can actually see how many LAU units are involved, which is really interesting. You can see here the LAU units. There is 4 of them, and but what I would like to show you here is how many of those instructions is supported by CPU. So let's take a look actually. Now let's take a look how many instructions, how many pages. And this is way more than 100 already. It's like hundreds and hundreds instructions. this is not reduced instruction set anymore. ARM is really complex. ARM has hundreds and hundreds instructions actually. And yeah, so this is simple evidence that the ARM is really not simple or reduced instruction set. So now let's take a look on the IPC advantage, which is bringing the better instruction set like ARM. So let's take a look. According to my findings, it's approximately 20% higher IPC just because the ARM instruction set. And let's take a look on some data. We already talked about the number of the registers, which actually avoids some shuffling the data from on and off, and you can see here, but the compiler doesn't see actually the physical registers. So actually, then the code is on the x86 is using more load and store instructions. And you can see it here when we compare actually ARM and x86 here. You can see that for the same amount of the work, ARM needs less load and less store instructions than x86. x86 needs much more load and store instructions, and this is due to less available registers. Even if this is eliminated by microarchitecture and using the physical registers and some logic, actually the binary code is kind of spoiled or not effective, and it costs you energy and the transistors in the microarchitecture. So yeah, do not underestimate really good instruction set, because this is a typical example where you can save a lot of instructions and a lot of transistors and energy, and this is the typical here. And you can see also ARM is kind of heavy for the branching, and x86 needs less branching. And but in overall, you can see here, this is actually the LAUs, this is the execution. This is where the calculation is done actually. So this is the LAU and floating point operations here together. So you can see ARM has more time to be spent on real calculations than x86. I mean, not much. But for example, here in the floating point spec benchmark, it's pretty significant. And actually, there is no comparison where ARM is actually worse. There is always maximum is the same, like this integer spec. Here is like a 50-50. And but in terms of this shows that the ARM should actually provide actually higher IPC than x86, just because of the instruction set. And I found really good study which really compares alpha architecture, digital alpha architecture, ARM and x86. And there is a lot of graphs. There is a lot of really interesting graphs which is showing really some memory shuffling in x86. So there is a lot of graphs, but I just took this one, which is probably showing that which is the most important. And it's interesting because they did a mathematical model of the Intel Haswell CPU, and they made it with different front ends. And there is also ARM front end and digital alpha front end. And you can see the Intel Haswell with the ARM instruction set. It provides this blue, it's like in average like a 20% faster, like a 20% higher IPC, just because the ARM instruction set. Interesting thing on this graph is that x86 is not really bad architecture, because when you compare the x86, which is this red line, this is the x86 baseline Haswell, and you can see that in compared to Haswell on alpha architecture, yeah, sometimes it's sometimes worse, sometimes a little bit better, but sometimes worse, sometimes really much worse than the x86. You can see here. And the floating point, yeah, it's like something like this, sometimes worse, sometimes bad. So x86 is not a bad instruction set. So in terms of performance and the IPC, it does pretty good job. Because don't forget, Alpha was the high performance server architecture. Well, it was killed by Intel. The Compaq sold it to Intel, and Intel killed the legendary EV8, which is the 8LAU SMT4 CPU. It was developed in 2000. And so it was killed by Intel. Intel took all the patents, of course. And so the alpha instruction set was really high performance. So x86 is doing a really good job here. So don't forget that just the ARM is so much better. This is the only conclusion here. So when I get to all of the data and I started to realizing that the ARM is so much better than x86 actually, I was like asking, how is that possible, you know? And when you take a look on the date the ARM was released and developed and designed, you can see it was 2011 instruction set. So it was brand new instruction set, released 2011, in compared to x86, which has a root in 1978, guys. So it's a huge difference. It's like a 33 years difference, which is like a couple of centuries in the real life. So in the IT, the time goes much faster actually. So yeah, the designers, they just took really the best things from all the architectures probably, and they created the ARM. ARM v8 is really super powerful, and this is because it's really modern. And if you take a look on the evolution, x86 here is ARM64, and then they are adding some really useful high performance instructions. I like actually the AMD secure memory and total memory encryption of Intel. Is quite good actually for the security, and ARM is also bringing memory tagging extension, which is also dealing with some security in the C and C++ code, which is really good. So, but I would like to point here that the ARM is evolving pretty fast. And you can see that this Maxwell, the Thunder X, they actually have a special instructions which was suggested by Cavium Thunder X for the Thunder X2 CPU, and 8.2 is like kind of generic from the ARM. Then 2016 was the floating point matrix multiplication. It was because the Fujitsu supercomputer. And Apple asked for ARM v3, and 8.4 was also Apple extension because no other CPU has those instructions. 8.5 also is using Apple, and 8.6 is also Apple which has a general matrix multiplication in the basic instruction set. This is a huge thing. Plus SVE2, which is kind of removing neon. And the huge thing is also ARMv9. We know that the Makalu core will be only 64-bit. So ARMv9 might be throwing away 32-bit compatibility, unless the x86, they are still keeping 16-bit and 32-bit backward compatibility. But ARM is throwing away the backward compatibility here in the name of high performance. Every single transistor will be used for the 64-bit performance only, no 32-bit wasting transistors, whatever. So you can see there is a different philosophy between the ARM and x86. So ARM is not some small, simple architecture. This is really, you have to understand that the ARM is aiming for really high performance, and while x86 is still kind of bothering with the old 16-bit, 32-bit backward compatibility, which drags their day down, ARM is throwing away backward compatibility and aims for the high performance. This is a huge thing. This is really need to know before we go for the floating point comparison, because there are huge things in the floating point. So now let's talk and compare the floating point and the single instruction multiple data. It's not only floating point, because these SIMD units, they can also run the integer vectors. So let's call it SIMD units. To compare x86 and ARM, right now ARM has a 128-bit neon units, the instruction set, which is kind of DSP and vectors for the floating point, and the integer, which is kind of really similar to the SSE kind of. So kind of Zen 2, the modern x86 CPUs today, they have an advantage because they are mostly using 256-bit AVX, right? But actually, since next year, the ARM V1, the server core, is going to use SVE instructions extension. This is scalable vector extension, which is actually up to 2048-bit wide SIMD units. And it's kind of radical and new because they support variable hardware floating point width. And because x86, the IVX has a no variable. This is like a fixed. It's 512-bit or 256-bit, and there is no variability. You cannot run on some small CPU. You cannot run 256-bit instructions on some Atom core which has only 128-bit. This is not possible on the x86, but this is actually possible on ARM. ARM can run there is a same binary code which will run on a 128-bit floating point unit as well on 2048-bit hardware unit. And because ARM here did great, absolutely different philosophy. Actually, they decoupled the software from the hardware unit here. So it's it's pretty good job. So I was pretty amazed that the ARM has a much better actually the floating point instruction set, and the whole philosophy is much more flexible and much better. And not only by this they decouple, they have also the sizeless type actually. When you run the code, when you create the code, you don't care about the size of the vectors, because you will just say what to do with the vector, and it will be done according to the length until the vector is whole processed. So this is kind of different philosophy of the programming also, which is much better actually than the old one. And also matrix multiplication here. This is a huge thing. This is like going from scalar to vectors. This is like adding another dimension. And according to Intel, it's like a matrix multiplication speed up brings up to 10 times more performance. And this is huge. And this is really huge benefit. That's why it's really important for the performance, for the high performance servers and the supercomputers. That's why the Fujitsu ARM A64FX is actually beating NVIDIA GPUs. The CPU is able to beat GPUs, but only when using matrix multiplication and really smart instructions. So you can see this is the power of a lot of instructions which x86 used to have, like 1300 instructions, but ARM is actually taking the lead here and has a better instructions for the high performance computing than x86 here. So ARM is not ARM is really pretty impressive. Now let's talk about the subsets, because every SIMD extension has a different options. So let's take a look on the subsets. And you can see here the AVX has a 17 subsets. And if you want to see, you can go to the Wikipedia, but you will find on the end of the page this table. And this is the typical, this actually explains the problem why AVX512 has a problem to become a new standard and spread out. Because you can see every CPU beginning as Skylake X has a different subset support. Cannon Lake added something, but the Cascade Lake removed some functionality. You know, they removed some subsets and added something else. And it's really strange. And only the bfloat 16, which is really useful for the machine learning. This is a big thing actually. And also ARM is going to support it since next year, the bfloat 16. So you can see only Cooper Lake here is supporting the bfloat 16. And but strangely, Ice Lake and Tiger Lake, they increased the support, but they are not supporting bfloat 16. So even Tiger Lake, which is the newest architecture from Intel, it doesn't support them all. And that's a quite big problem. And it could be, I hope that AMD Zen 3 can support them all, which would be great in compared to Intel, because they can kind of be better than the Intel for supporting everything. But actually, this is the problem. There's 17 different subsets, and a lot of CPUs, everyone supports different subsets. And in compared to ARM, they have only one optional subset. And so it's really simple. So they really push for the standardization here. So let's take a look on the SVE2. And this is the graphs from the ARM official. And you can see the neon is 128-bit wide. So, and you can have also SVE that you need only 128-bit wide. So, but you can see here there is a 20% performance increase just because better instructions, and also decoupling the software from the hardware. So, and you can see that 256 bit it can double actually the floating point performance here. And 512 bit, yeah, it's not doubling, it's only 3.5. So you can see 256 is kind of a sweet spot for the efficiency. And we can probably see the modern, the new ARM cores, they will have a probably like a 4 floating point units, but probably only 256 bit wide. The only CPU which is using 512 is actually the Fujitsu, but this is the supercomputer. This is kind of monster for the floating point. So yeah, this is using 512, and even in the future can use up to 2048. So for the supercomputing and for the Fujitsu, yeah, there might be something even wider in the future. But for the smartphones and the servers, the Neoverse, they will probably stick with 256 bit wide for a while. So I was very impressed of what I found for the data when I comparing the ARM and x86. And this leads me to some conclusion. And the conclusion is that ARM is really, surprisingly for me, is much better than the x86. And to summarize it, it has twice as much architecture registers, which leads to the higher IPC, which we can see in the in the performance in the Geekbench. We can see that the Apple cores has like a 70% higher IPC than Intel, and also AMD, because AMD is plus minus 5%. And yeah, the next thing is ARM is kind of based on the RISC with the fixed coding, which brings energy efficiency and makes the architecture really simple. So you can actually have more transistors for the execution units, which makes the performance and the calculation. And x86 has a lot of transistors spent for to deal with the old instruction sets, a low number of the registers, and the variable, the front end must be really hell actually. And yeah, we found that there is a 16% larger binary for the ARM. This is kind of penalty. But Apple again has a memory compression, which turns that small 16% disadvantage into a huge benefit because of the memory compression. Yeah, it's and for the floating point, ARM has a 2048-bit wide support for the floating point, and also it has a matrix multiplication, which is the huge step forward, because this is the scalar vector matrix, and even later on will be spatial, like an n-dimensional. It's not vector is a one-dimensional, matrix is the two-dimensional, and spatial is like n-dimensional. So we will see a lot of development in this area, I think, in the future. So matrix multiplication is just the beginning, and ARM is the leader here. This is a big thing. And so there is, yeah, the summary is that ARM is very complex. And a lot of people is probably surprised how ARM is really complex, how many instructions is there, and how advanced actually it is. So it's funny that most people is probably influenced, and I was also. 1 year ago, I thought that the ARM is really some simple instruction set, which is good only for smartphones, which are kind of simple device, for the efficiency, whatever. But since I tried to search and I found this data and the graphs, Well, I'm pretty convinced that ARM is really attacking the servers. ARM is probably much better instruction set than x86. This is my conclusion. You might have a different conclusion, but yeah, try if try to convince me and give me some better source into the comments if you want, and I can make some new video about this. But so far, I found that ARM is really impressive. The last thing I would like to talk about the future actually, and how x86 can fight ARM. And I think it's pretty difficult because I already talked that the ARM v9 is actually only 64-bit and no 32-bit compatibility, and probably also no Neon compatibility. So it will be using only SVE2 and probably TME, MTE, and some other things. So it will be like a new standard and throwing away the backward compatibility. So aiming purely for the performance. And I can see that the ARM is so much better and energy effective. I'm really wondering that how x86 can fight, because x86 has some options, right? They can do release like a new standard, like AMD64 did. So they can increase the architectural number of the registers. They can go 32 registers when they do some new update. But yeah, this would help for the IPC definitely, because they do increase the registers here with the AVX. But they can somehow increase here if they do some new standard. But I think what x86 cannot do is actually to deal with the variable coding. Variable coding, I think, is the biggest problem for x86. And it burns a lot of energy and the transistors. And all the development of the CPU is much more difficult, much more complicated front end. Yeah, I don't know. And this is actually hardwired in the architecture since 1978. And this is probably the biggest problem, and x86 this cannot repair. This is unrepairable, actually. And my conclusion, and it's kind of speculation, and this big question, if x86 can fight ARM. And my conclusion is this probably cannot fight and be better than the ARM, because it's just the CISC variable coding is so wrong since beginning, since 1978, because nobody knew that it's going to be so popular. So I think that the x86 cannot win over the ARM. ARM is much better from the design. It's much newer design actually. And I will just briefly take a look back to the IPC here, and you can see here that for example, Apple has a trend of the IPC like this. It's pretty clear that the IPC they can increase the IPC much better than the x86. Also, the ARM is it's even steeper, this curve. You can see they are running faster. They try to catch actually the Apple, and if you look at the V1 cores, the Makalu cores, you can see that the ARM actually is aiming for 2025 to reach the Apple probably. And when you take a look on the x86, like ignoring the P4, but you can see that the trend is like this, AMD, when we do ignore the bulldozer, but AMD is doing better job because they do Zen 1 actually, from Zen 1 they do Zen 2, Zen 3, maybe Zen 4. This is the prediction. Maybe AMD can do this. Intel with the Golden Cove can do something similar. But you can see here that this is different slopes. Even AMD and Intel, they will speed up, you know. They are still much slower than the ARMs they already provide, actually. And Apple is running incredible way, and I don't know. And my conclusion here is it has something to do with instruction set. Not only that, not only about number of the engineers or some better microarchitecture. And I think the ARM, because it is better instruction set, it allows them to use more transistors for the high performance and spend less time on the front end. So I think, yeah, x86 is really, the instruction set is limiting the IPC and the speed of the development. And if this is true, then it means the x86 will die. ARM will actually annihilate probably the x86. And this is my speculation, and but it looks like this. And yeah, it will be exciting actually for a few years, but I don't know. I'm kind of worried about AMD. I'm AMD fan, but I do worry about AMD because AMD did a big mistake when they cancelled K12.